Hi there. The purpose of this video is to help students find instantaneous velocities off of position time graphs. So we have a position time graph here. You can see that it's curving, which means that the velocity is changing or that there is acceleration. So what I'm going to do here is each one of these different times I'm going to try to draw a tangent line. My tangent lines won't look super great. It's kind of difficult to draw them on these tablets, these do accurate drawings. So I think that's my first tangent line. Oops. That's my first tangent line. So maybe call that V2. I call it 2 because it is at time equals 2 seconds. Okay, so V2 is delta x over delta t. So here we have which 10, so that's 15 minus 0. Yeah, 15 minus 0. That's 15 minus 0. 1, 2, 3, 4, 5. 5 squares is 2 seconds. So that's 15 over 2, which is 7.5 meters per second. Alright, next one. So call that V4. So I think that has a rise of 30. And the change time is 1, 2, 3, 4, 5 is over 2 seconds. So that's 15 meters per second. Next one. Alright, so this slope here, 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 50. So that's V6. 50 over 2 this time, that's 25 meters per second. And actually, I'll just do one more. So I got 1, 2, 3, 4. I'm kind of doing it in these certain numbers because just to make my counting easier. Alright, so this is delta x is 1, 2, 3, 4, 5, 6, 6.5, say. So 65 over 2 seconds again, so that's what, 32.5 meters per second. So then I have a data table, or I can create a data table now. Time, velocity, so I have 2 seconds, 4, 6, 8, and the velocities are 7.5, 15, 25, and 32.5. And if I wanted, I could graph that now. So actually I can use this online calculator to do graphing. It just makes things a little bit easier and more accurate. So it's www.desmos.com. Right, so I can add stuff here. I can add a table. So my x values, that's the independent variable. So that's time, so that's 2, then 4, then 6, then 8, and I didn't have another one. And this one is 7.5, 15, 25, and 32.5. So we can now then look at this graph. So there's my data points. I guess I'm kind of zoomed in too much. There we go. And we can actually, with this thing, we can even change what we're looking at. So I can say on the x-axis I only need to say from see from maybe minus 10 to positive 10. Actually, go minus 5 to positive 10. Oh no, that was the wrong one. Minus 5, positive 10, and y-axis minus 5 to say 40. There we go. That's our area zoomed in. And so there's the points. I could do a line of best fit. To do a line of best fit in this program, I could go y equals mx plus b, add a slider for that, add a slider for that. Like this. Something like that. So that's the equation of that line. So we get y equals mx, so the slope of that is 4.1, and this should, I think we can put that to 0. Just force it through 0. Yeah, close enough. So we can maybe say that the equation of that line is the slope is 4.1. So if we were to hand graph this, we could get the same sort of result. Tar graph, and the slope of that line would be y equals, b, that's a velocity time graph. Velocity equals 4.1 t, and that is the slope, and that is equal to acceleration. So that's even a little bit further than we've kind of gone in class. And that we could say then that this is the mathematical model for this graph that showed some, for this graph that showed an object accelerating.